Hi, Chem 240. This is a special video about the Clausius-Clapeyron equation, which can be a little bit difficult to understand and work with. So this is a small video that we're going to put in chapter 11 because that's where it's covered. So I have a pure liquid here, okay, and it's at a certain temperature, and you see obviously the individual molecules are these little dots, and they're all traveling because in liquid they have translational energy and they can move around. The ones that are close to the surface, though, if they happen to be headed upward with enough kinetic energy, they can actually escape the liquid. And that's what vaporization is, okay? It's not necessarily boiling. Vaporization is a surface phenomenon where molecules that are close to the surface and have the correct kinetic energy, enough kinetic energy to break free of the liquid, and also have the correct orientation. They have to be headed up towards the surface of the liquid. If you're just randomly headed down, you're not going to evaporate, right? In order to evaporate, you've got to have enough energy, so your arrow has to be big enough, and it has to be pointed in the right direction. So those of you guys who've taken physics already, this is a vector quantity, okay? It's a direction and a magnitude, so the direction has to be up, okay? So the Clausius-Clapeyron equation describes what happens to the amount of evaporation, or the rate of evaporation, okay, as a function of temperature. So when you heat this with a Bunsen burner, the temperature of the liquid's going to go up, the kinetic energy of the molecules is going to go up, and obviously the temperature is going to go up. And we specifically want to talk about the Kelvin temperature. The reason is the Kelvin temperature starts at absolute zero, and the phenomenon that we're going to describe works right through 0 degrees Celsius. So if we had an equation with a zero in it, okay, for 0 degrees Celsius, the whole thing would explode and the equation wouldn't work at 0 degrees Celsius, and it actually wouldn't work at any of the minus numbers either. So we need an equation that is a function of the Kelvin temperature only. Okay? Well, if you do an experiment, you will see that for any particular liquid, the graph of the Kelvin temperature on the independent axis on X versus the vapor pressure, the amount of molecules that are evaporating from the surface, would always look like a curve like this. So at a lower Kelvin temperature and lower pressure down here, right, at this temperature and this pressure, that point on the line would represent the vapor pressure, right? The vapor pressure would be the amount of pressure that's coming off the liquid from the liquid, okay? That's going into the atmosphere from the liquid, that pressure that's coming off, okay? Now remember, you also have a pressure based on the room. You have the air molecules and whatever, so that's the external pressure. So coming down over here, we have P external. Most of the time, we're at room pressure, right? So P external is 1 atmosphere of pressure if you're, like we are in New Jersey, at sea level. Okay, so the amount of external pressure pushing down on here is not going to affect the amount of molecules that evaporate. All that these two things are going to relate is a very special point when not only can molecules evaporate from the surface, but molecules can evaporate from within and create an imminent bubble. This would be boiling, right? When boiling is a tiny bubble forms, and the vapor pressure of the liquid pushing out on the edges of the bubble can maintain the bubble long enough that the bubble can be stable, it's less dense than the liquid, and rise to the top. Well, that is a very special place on this graph. When the vapor pressure equals the external pressure, and in our case, we're doing this in New Jersey, so it's going to be 1 atmosphere of pressure. If you were in Colorado, it would be a little bit lower. So at 1 atmospheric pressure, what temperature do you need so that the vapor pressure would be equal to the atmospheric pressure? That special position on the graph right here, this pressure and this temperature is called the normal boiling point. Okay, for water, when the atmospheric pressure is 1 atmosphere, water boils at 100 degrees. Why? Because that is at 100 degrees Celsius, right? Which is 373 Kelvin. So this would be 373 Kelvin if we were doing water. At 373 Kelvin, the vapor pressure coming off of the liquid would be equal to 1 atmosphere. So that not only would this pressure coming off here be equal, any bubbles that started to form would be formed with a vapor pressure inside them of 1 atmosphere. That means they wouldn't get collapsed by the external pressure. Now, if you have a very deep column of water, like 50 feet down, then it's much harder. You're not going to boil that water because not only do you have the pressure from the atmosphere, but you have the pressure from the weight of all the water, right? So this only holds for like a pot of water on the stove where it's just, a few inches, 4 or 5 inches, where the weight of the extra water doesn't come into play, right? You're not boiling water at the bottom of the ocean at 100 degrees Celsius. How come? Because the external pressure is not just the pressure of the atmosphere, it's the pressure of all the weight of that water. Okay? Good. All right, so that's the only thing where boiling comes in, is that very special place. But this relationship, this curve, holds for every substance. So if this is water, here's ethyl alcohol. Here's another chemical, chloroform. They all come upon differently on these graphs, but they all take the form of a curve. Well, scientists now know how to fit curves, and they can do math with curves. Turns out that a curve like this is exponential. And if something is exponential, you would say, hey, you know what? I have an idea what this formula would look like. It probably would look something like this, and I bet you would guess it, right? And I don't know why we just don't teach it to you this way, but the vapor pressure would be equal to E, right? Because E is nature's number that things go up exponentially at, as opposed to 10 to the x or 2 to the x. It's E to the x. And E would be raised to some constant, right? Some constant times T. So some constant, I'll call it CT. And this kind of equation would describe that. Well, we know, it turns out, what C is. So the vapor pressure could be described as E, and then this constant up here turns out to be delta H of vaporization over the gas constant R, all times T. So you could just use this equation like this. This, guys, would describe this. And we could do everything we wanted to with this. But I guess chemists like to straighten things out, just like physicists. And the way to straighten this equation out is to not take the vapor pressure of something, but take the natural log of the vapor pressure. Why the natural log of the vapor pressure? Because the natural log is kind of the reciprocal of E. So the natural log times E cancels out, and this whole stuff comes down into the numerator. Okay? And for a reason that I can't explain, they don't graph this versus the Kelvin temperature, they graph it versus 1 over the Kelvin temperature. So as you're going to the right over here on this graph, the Kelvin temperature is going down, so the vapor pressure is going down. So this is the lower temperature, lower pressure point. This point over here is this point over here, right? Lower temperature, lower pressure. The log of the vapor pressure goes up with the vapor pressure. But 1 over T is going to be reciprocal to T. So here's the higher temperature point, here's the lower temperature point. So the whole reason for deriving the Clausius-Clapeyron equation is to straighten out this line. And here's what it looks like. When you take the log of it, you get the natural log of, don't worry about the 1s and 2s, but this will be 0.2. So I can describe any point on the line as long as I know it's delta H of vaporization. Okay? And if I know the temperature, T2, I can calculate P2 through this equation. So this is just the linearized version of this. Well, B, the intercept of this graph, doesn't have much meaning to us. So let's get rid of it. How would you get rid of an intercept that you don't care about? Well, the way to get rid of an intercept is to make a 2-point formula. So here's the 2-point formula, and then I'm going to work on it with you. We'll do a sample problem. Now, you're not going to have to do any derivation like this. This is just for the people who want to understand the math better. Well, if I want to find out, right, what's going on here, the change in the vapor pressure divided by the change in 1 over T, what could I do? I could subtract this equation at 2 different points, okay? So watch, at this higher point, P2, T2, the equation will work because here's P2 and T2. Delta H for the vapor pressure is a constant. It's related to the slope of this line. The slope of this line is minus delta H over R. Okay. So that's the slope of the line. Oh, you have a minus sign in here, so I don't need a minus sign. Sorry. It's just H over R. Delta H over R. Okay, so what can I do? I can subtract the second one off at a different point, and what that's going to do is going to eliminate the b's, because the b is the intercept. Both points are on the line. The b is going to be common to both, and obviously the b is going to be up here. So how are we going to get rid of the y-intercept in our equation? The way we're going to get rid of the y-intercept is we're going to subtract the formula with these points plugged in and these points plugged in. So we'll take the 2's minus the 1's, because this is usually, we refer to the 2's as the one further on. This would be the final temperature and the final pressure, the initial temperature and the initial pressure. Okay, so we do this a lot. This is the way we create a 2-point formula. So I'm taking the second version minus the first version. Okay, this one minus that one. Okay, well, when I do that, what happens? Well, this minus sign, the plus b minus a minus sign, so the b's cancel out. Everything else stays. So I bring this over here, ln of P2 minus ln of P1. Right, I just rewrote it. That's the left-hand side of the equation. The right-hand side of the equation, okay, I just rewrote it. Minus delta H over R, 1 over T2, minus, just like here, minus delta H over R, 1 over T1. Okay? So the next thing I could do here is factor out delta H over R. Okay? So when I factor out delta H over R, that comes out in front, and I realize that this minus sign and a T2 is in the front, and a minus 1 over T2 is in the back. What's a minus times a minus? That's a plus. Well, that looks awkward. Why would we put the minus 1 first? Usually we have an entity, 1 over T1, and we subtract off this other entity. So that's why you shift it around. That's what causes the Clausius-Clapeyron equation to be reversed. To get rid of this minus sign back here, you take 1 over the T1 minus 1 over the T2. Okay? And then last thing you could do over here, if you remember from the rule of logs, subtracting one log from the other is the same thing as the log of that quantity divided by the log of the other quantity. So this in here is the same as this up here. So you get this nice simple little equation. Now what is this for? Why would you do this? Okay, if you know delta H of vaporization, how much enthalpy it takes at constant pressure to evaporate the liquid at one particular temperature and pressure, you can calculate it at any other temperature that you're interested in. So there are 5 variables here: 2 temperatures, 2 pressures, and delta H of vaporization. Okay? You are going to have to be given 4 of them, and you have to calculate the 5th one. Okay? Last thing I want to say about this. These temperatures absolutely have got to be in Kelvin. You will get it wrong if they're not. This thing will explode if there's a 0 in the bottom, and even if there's not a 0 in the bottom, it'll give you junk. Okay? R is just the gas constant in energy units, so you're always going to just put in the same number. The gas constant in energy units is 8.31 joules per mole Kelvin, so that's not going to change. I'm not going to ask you to calculate R. That's the R that you want to put in. In the numerator here, if I give you the delta H, In kilojoules per mole, you have to change it to joules so that it matches up with this one, and the joules will cancel out. The energies have to cancel out. So if you're given delta H of vaporization in kJ per mole, or kJs, sorry, it would be kJs per mole, okay? If you're given to in kJs per mole, kilojoules per mole, you need to convert it to joules per mole. So that means multiply by 1,000. So that's important. Okay, so I could give you 2 temperatures and 2 pressures and ask you to calculate delta H of vaporization. It'll come out in joules naturally. Then you can just change it to kilojoules because it'll be so big. Or, what's more likely, I can give you delta H of vaporization, 1 set of temperatures and pressures, and ask you what is the vapor pressure at a different pressure. So the different one, let's make that P2. We don't have a beginning and an end. We have the one that you're interested in as P2. That'll be great because in the numerator, you will have what you're solving for. So usually make the pressure that you're interested P2, not P1, right? The one that you want to find, and that'll make the math a little easier. Okay, let's do a sample problem, okay? Now remember, I could always make these tricks, and the trick that all chemistry teachers like to ask you is instead of just straight up giving you 2 pressures and 2 temperatures, they talk about the normal boiling point. So you have to realize, wait a minute, I don't have the second pressure. How can I do this? Well, if you have the normal boiling point, if somebody gives you the normal boiling point, like in this question, the pressure that the normal boiling point is always associated with is 1 atmosphere, or if you're doing it in torr, 760 torr. Remember that from chapter 10, 1 atmosphere of pressure, sorry about that, 1 atmosphere of pressure is the same as 760 torr of pressure, or 760 mmHg, millimeters of mercury. I won't give you inches of mercury or feet per inch squared, or any of those other ones. Those are the only 3. A torr is the same as a millimeter of mercury. 760 torr or an atmosphere. Okay, go back to the formula for a second. I should make one more point. The pressure units that you use here don't matter. You just have to be consistent. You can do these both in atmospheres. You can do them both in torr. Just be consistent. If you put this one in torr, and you're solving for the other one, that one will come out in torr. If you put this one in atmospheres, that one will come out in atmospheres. Just be consistent, because they have to cancel out. Units have to cancel out. Okay, back to our question. Let me make the screen a little smaller, and let's solve one of these. Okay, calculate the vapor pressure of an unknown liquid at 25 degrees C if the normal boiling point of the liquid is 61.7 degrees C, and the vapor pressure is 31.4 kilojoules per mole. All vapor pressures, guys, are going to come out to be positive numbers. It always takes energy to evaporate something, right? It's an endothermic process. So these will always be positive numbers. If you get a negative number, you did something wrong. And they're usually about this size, 30, 40, 50, 20, something like that, kJs per mole. Okay, first thing. Normal boiling point. Click in your head right away. Normal boiling point. What does that mean? That's the boiling point at 760 torr. So my first set of numbers, my T1, P1, the ones that I know are 61.7 degrees. I have to change it to Kelvin, so I add 273. That gives me 334 Kelvin. And what pressure does that? That's 25. Excuse me. That's the 61.7, right? So at the boiling point of 61.7, that temperature, that boiling temperature in Kelvin is 334. And what pressure does that correspond to? 760. So that's my first set. I have a set of temperatures and pressures to plug in. That's my T1, P1. Okay? All right, what else do I have? I'm interested in the pressure, vapor pressure at P2 below the boiling point. Well, remember, even though it's not boiling anymore, the liquid is still evaporating from the surface. So my expectation is P2 is going to come out lower than P1. It's going to come out lower than 760 atmospheres, or lower, 760 torr, or lower than 1 atmosphere. right? So that's what I'm predicting. P2 is lower. Why? Because T2 is lower. Okay, what is T2? Well, we want to calculate it at 25 degrees C. We have it at 61. We want to calculate it at 25. But again, my T2 has got to be in Kelvin. So take 25 plus 273 to give me 298. Why do I have P2 here equals question mark? Because that's what we're solving for. Okay, plug everything in. Okay, where does this 34.1 times 10 to the third joules per mole come from? That comes from the vapor pressure they gave you. Why did I multiply by 10 to the third? Well, 10 to the third is the same thing as 1,000. That's the conversion between kilojoules and joules. This numerator has to be in joules to cancel the R, which is in joules. So goodbye joules. You want this coefficient here to have no units. Or actually, it's going to have the units of temperature, which is kind of cool. Okay, moles cancel out, and right now this whole thing is 1 over Kelvin. Okay, what's 1 over Kelvin? Kelvin. Okay, so all of this stuff here, you've got a Kelvin in the denominator of the denominator. This whole thing comes out to 3,779. That's what you get when you get this divided by this, and it has a unit because the kelvins didn't cancel out. It's got kelvins in the numerator. Okay, here's our two 1 over temperatures. Plug them in my calculator. You can use memory. You don't have to write them down. If I take 1 over this number, I get this. What unit does it have? 1 over Kelvin. 1 over 298, I get this. When I subtract them, this second one is bigger than the first one. That's why I get a negative sign. Okay, notice this is 10 to the minus fourth. And when I subtract two numbers, first of all, you can only subtract numbers that have the same unit. Well, that's okay because they both have the same unit, and the unit is 1 over Kelvin. So this minus this gives you negative 3.68 times 10 to the minus fourth times 1 over Kelvin. Well, last piece. I've got this coefficient in Kelvin, this coefficient in 1 over Kelvin. Multiply the numbers. The two units cancel out. This whole right-hand side of the equation is dimensionless. All the units cancel out. Well, that makes sense because this side is dimensionless. All these units would cancel out too. A pressure over this pressure in the same units, they would cancel. So you're going to get just a ratio here. Okay? So right now, I have ln of P2 over P1 is equal to negative 1.39. Okay, well, I don't want ln of P2 over P1. I want P2 over P1. So how do I get rid of the log of something? I take the anti-log of both sides. Well, the anti-log, guys, is E. So on your calculator, you could raise E to the negative 1.39. That's how you get from here to here. Okay? Some people would write it like this. ln P2 over P1 is equal to negative 1.39. And then say, oh my God, how am I going to get rid of the ln over here? I'm going to take ln to the minus 1, which is E. Right? Those two things are the same thing. And then the anti-log of this side, which is E. So the anti-log of the log cancel out, and I get the anti-log, the anti-natural log of that. Well, that's the same as E to the minus 1.39. Your calculator has a button E, and you want to raise it to the negative 1.39. Okay? All right. I'm going to do it for you, but this ratio, we're just going to leave it as a ratio. We know P1 is 760 torr, but I'm going to leave this as a ratio for a second, and let's just get what that ratio is. Well, if I take E to the minus 1.39, I get 0.249. This has meaning right here. P2 over P1 is the ratio of the new pressure to the old pressure. Well, guess what? The new pressure is a quarter of the old pressure. Why? Because the ratio is 0.245. Well, guess what a quarter is, guys? 0.25. So to me, this is 0.25. So the new pressure is a quarter of the old pressure. So last step, I want to find out what P2 is. What is the vapor pressure of this gas, this unknown liquid, evaporating? I get my ratio here times P1, which I know. Here's my P1, 760. Plug it in. This has no unit. times something with torr gives you torr, right? Dimensionless times torr gives you torr. So 0.249 times 760 torr gives you 169 torr. Well, that was our expectation. Okay, our expectation is the new pressure, the pressure here, right, at 25 degrees should be much lower than the pressure at 61 when it was boiling. So for this particular case, we had the pressure at the normal boiling point, so this was 61 degrees Celsius. This at 25, the vapor pressure is going to be much lower. It's going to be 25% of the old one. So these things are going to go down quickly. Okay? All right, last thing I promised. Let me see if I can get my calculator, and let me do this part for you so you trust me, you believe me. Okay? So what I'm saying is, I'm going to do this for you. E to the negative 1.39. Okay? So on my calculator, oops, I'm going to need a little more light because my eyes aren't that good. I'm old. Here you go. On my calculator here, maybe I gotta shut the light off for you guys, make it bigger. ln is the natural log, here's e to the x, okay? So what I'm gonna do is I'm gonna hit shift ln, which will give me the little yellow stuff, e to the x, so I get e, and then all I have to do is raise it, so do a little caret sign, change the sign to negative, raise it to the negative 1.39. Let's try that. Oops, syntax error, so I must have put it in wrong. Try it one more time. Let's do this. Negative ln e. I don't think I'm going to raise it to, I'm just going to say e, and I'm going to put negative 1.39, and that's all I had to do. So when on this calculator, don't raise it to that. They assume when you put e in, you want to raise it to that number. So I get my 0.0249, which is basically 25% or a quarter, right? And that's where that came from. And the next step is easy. We have this number. This could have been a 760 down here. So cross multiply, and now you got P2 by itself. Good? All right. Hope that helps. That's the Clausius-Clapeyron equation, soup to nuts. Okay? The only other thing I could do is it would be easier. Usually people don't ask you for one of the temperatures. They usually ask you for one of the pressures. I could give you two pressures and two temperatures, right? One set of P1, T1 and another set of P2, T2, and you could calculate delta H of vaporization. That's a little easier. Okay? And again, it's going to be careful. It's going to come out in joules per mole. Okay, so you might have to change it to kilojoules per mole depending on what the question is asking for. All right, let me make this a little smaller so you can see the whole thing on one page. Okay, some of my notes has these as log, the log base 10, and it has a 2.3 here. But you guys all have modern calculators that have the natural log, so I'm going to teach it to you always just with this formula here. Okay. Later on in the course, we're going to see another formula in kinetics that's very related to this, okay? Almost has the same form. It just talks about the rate in which chemical reactions take place as a function of the Kelvin temperature versus this one, which talks about vapor pressure or things evaporating, but it has the same form. That one is called the Arrhenius equation. It's going to be in chapter 14. This one is called the Clausius-Clapeyron equation. It's in chapter 11. All right. Talk to you next time.